Common experience indicates that time passes just as quickly for a person standing on the ground as it does for a person traveling across country on an airplane. For speeds much less than the speed of light, any deviation from equal times is imperceptible. However, at relativistic speeds, we will now show that the times are different, a result that is profound, if not shocking. We can see how this curious effect arises with the help of a light clock, which uses a pulse of light to mark time. A short pulse of light is emitted by a light source, reflects from a mirror at the top, and then strikes a detector that is situated next to the source. Each time a pulse reaches the detector, the clock registers a click, another short pulse of light is emitted, and the cycle repeats. Thus, the time interval between successive clicks is marked by a beginning event, the firing of the light source, and an ending event, the pulse striking the detector. The source and detector are so close to each other that the two events can be considered to occur at the same location. Suppose a light clock is placed aboard a spacecraft that travels at a constant velocity relative to the Earth. The astronaut is at rest with respect to the clock on the spacecraft and, therefore, sees the light pulse move along an up and down path. According to the astronaut, the time interval delta t0 required for the light to follow this path is the distance 2d divided by the speed of light, c. To the astronaut, delta t0 is the time interval between the ticks of the spacecraft clock, that is, the time interval between the beginning and ending events of the clock. Now consider an Earth-based observer for whom the spacecraft moves by at some speed that is a significant fraction of the speed of light. During the time it takes a light pulse to travel from the source to the mirror, the ship moves to the right. The light must therefore take a diagonal path according to the Earth-based observer, otherwise it would miss the mirror. Of course, since the light pulse hit the mirror in the astronaut's frame of reference, it must also hit the mirror according to the Earth-based observer. So the light follows a diagonal path to the mirror, and the same happens on the return path to the detector. It is clear that the diagonal path is longer than the direct up-down path seen by the astronaut. So what, you might ask? This was easily reasoned out by simple kinematics and geometry. The interesting result arises when we apply the speed of light postulate of special relativity, that is, that the speed of light is the same in all inertial frames of reference. That means that the speed of light is the same, c, for the astronaut, for the pulse that he sees taking a shorter path, as it is for the observer on the ground, also c, who observes the same pulse taking a longer path. That means that the pulse takes longer to complete its path for the ground-based observer. This means that the time between ticks of the clock is greater as observed for the ground-based observer, delta t, than for the astronaut on the ship, delta t0. We sometimes summarize this result by saying, moving clocks run slow. This is known as time dilation. We can analyze the geometry of the moving light clock in order to find a relationship between the times experienced by the two observers. The vertical separation between the light source and detector on the floor of the ship and the mirror on the ceiling is d. We can label the beginning event as the firing of the light pulse and the ending event as the light pulse striking the detector. The ship travels a horizontal distance L as the light pulse travels from the source to the mirror, and another distance L as it travels from the mirror to the detector. And, in each leg of the trip, the light follows a diagonal path of length s. We can identify a right triangle that relates these distances as s equals the square root of d squared plus l squared, or 2s equals 2 times the square root of d squared plus l squared, which must be equal to c times delta t. Squaring both sides and solving for delta t gives delta t equals 2d divided by c times 1 divided by the square root of 1 minus v squared divided by c squared. But 2d divided by c equals delta t0, the time experienced by the astronaut on the ship. So we write delta t equals delta t0 divided by the square root of 1 minus v squared divided by c squared. And this is called the time dilation equation. Note that the denominator is always less than or equal to 1, and therefore delta t is always greater than or equal to delta t0. The time interval delta t0 is called the proper time interval, which is the interval between two events as measured by an observer who is at rest with respect to the events and who views them as occurring at the same place. In the case of the observer on the ship, the light emerges from the source and strikes the detector at the same place in his frame of reference. The time interval, delta t, is called the dilated time interval, which is the interval measured by an observer who is in motion with respect to the events and who views them as occurring at different places. In our case, the observer on the Earth saw the light emerge from the source at one place and strike the detector at a different place, a distance 2L away. Finally, v is the relative speed between the two observers, and c is the speed of light in vacuum. As a simple example, suppose a spacecraft moves past the Earth at a speed that is 0.92 times the speed of light. The observer on the ship measures the time interval between clicks of the onboard clock to be 1.0 seconds. What is the time interval that an Earth-based observer measures between ticks of the spaceship's clock? We start with the time dilation equation and input the speed in proper time delta t0 equal to 1.0 seconds. This gives delta t equals 1.0 seconds divided by 1 minus 0.92 c divided by c squared, which equals 2.6 seconds. What does this mean? This means that for every second experienced by the ship-based observer, an Earth-bound observer experiences 2.6 seconds. This has profound implications for space travel, as these proportions can be extrapolated to larger time intervals. For instance, if the ship-based observer travels for 10 years according to their clock, the Earth-bound observer measures a time interval of 26 years. And these proportions get greater as the relative speed between the observers increases. Time dilation has been tested and verified through a number of experiments. In one case, high-precision atomic clocks were synchronized with land-based clocks loaded onto jet airplanes and flown around the Earth. The differences in the measured times were consistent with time dilation. In another case, the difference between decay times of certain particles at rest and moving at high speeds were measured, and the differences were again consistent with time dilation. Also, time dilation has to be accounted for in the use of the global positioning system. Finally, it should be noted that time dilation is real and not just a perceived effect. Biological processes actually occur at different rates in different inertial frames of reference. It is curious that time dilation may one day allow humans to survive trips of great distances that would otherwise not be possible because of our finite lifespans.